Hi everybody, this is Professor Turner with Purdue Polytechnic Institute, and I just want to welcome you to ECET 364, our course in the Fundamentals of Electromagnetics. This is a course that's going to investigate the what's called the electromagnetic phenomenon, which is really the propagation of electromagnetic waves through materials, and in particular the application of the physics of electromagnetic wave propagation to electric circuit analysis and design. So really what we're talking about is we may have some source of radiation. It's going to cause an electromagnetic wave to propagate. And broadly that occurs in two situations. One is if we have a conductor, such as a piece of copper, and we apply a voltage to that conductor. What's going to happen is an electromagnetic wave is going to propagate it. You know it as a current and voltage wave. I'll tell you that that's a little bit of a simplification. What you've learned previously is a little bit of a simplification. We're going to expand upon that in the class and really understand in detail what's happening on this conductor as the voltage and current propagate sinusoidally through the conductor. And the second situation in which you might see that is if this point source of radiation is an antenna, in some sort of wireless device like a cell phone or such thing. So today's video is really just kind of a short introduction into the nature of the electromagnetic wave phenomenon. And broadly, what we're talking about is that electromagnetic radiation it's a format or a method through which all energy travels through a medium such as a conductor or a vacuum by establishing oscillating electric and magnetic fields. These two fields, which we call the E field and the B field respectively, they're interdependent fields, meaning that their existence is predicated on the existence of the other. You can't have one without the other one. And their nature is fully described mathematically by a set of four equations developed by James Clerk Maxwell. And these are called Maxwell's equations. Although it isn't immediately obvious from these equations, but Maxwell's equations show the relationship for all electromagnetic phenomenon. They describe light, they describe electricity, any sort of E&M phenomenon. So, they're often used in electrical engineering, they're often used in physics. They apply to DC circuits, they apply to AC circuits, they apply at low frequency, at high frequency. And believe it or not, they can actually be used to derive every law of electrical engineering. This includes Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law. So in a sense, Maxwell's equations are kind of the grand unifying theory that describe all electrical phenomenon and magnetic phenomenon that we've observed in nature. I'm going to go through Maxwell's equations real fast and just describe them to you. It's not important that you understand the mathematical formalism at this time. I just kind of want to describe them and, kind of just get them out there for your consumption. So the first of Maxwell's equations tells us that the divergence of the electric field is equal to the charge density rho divided by the electric permittivity of whatever material the charge is in. And what this is saying is that if I have a positive test charge, like a proton or something, it's got electric field lines that come off of it and point away radially. Kind of the rate at which these electric field lines leave is called the divergence of the E field, and how many of these lines are is determined by the charge density divided by some material property, electric permittivity. Maxwell's second equation says that the divergence of the magnetic field is zero. What that is observing is that magnetic materials always occur with plus-minus pairs. You can kind of think of a bar magnet. And magnetic field lines always start on the positive terminal of a magnetic material and end on the negative terminal of a magnetic material. And basically what this divergence statement is saying is that there are as many field lines leaving a magnet as there are coming back. So if I have one that leaves, it has to come back. If I have one that leaves, it has to come back. And so the divergence, which is the total count of things leaving the magnet, is zero, because 1 minus 1 plus 1 minus 1. So you see the net result is that there's zero divergence there. So Maxwell's first two equations are basically statements on the nature of electric charges and on magnetic materials. let's move on to Maxwell's third equation. What Maxwell's third equation states in mathematical terms is that the curl of the electric field is equal to the opposite of the partial derivative of the magnetic field with respect to time. And that's really a mouthful, so I'm just going to say what this is trying to say is that if there's a change in the magnetic field strength as a function of time, it will cause a time variant electric field. The corollary to Maxwell's third equation is Maxwell's fourth equation, which says that if we have either a current that is flowing or we have a time variant electric field, it will result in a time variant magnetic field. So those are Maxwell's fourth equations. Again, don't worry about the mathematical formalism or any of the mathematical operators such as the del, the dot product, the cross product, the partial derivative. You haven't seen any of those yet. I don't expect you to know what they mean. Again, I'm just trying to get the concept of Maxwell's equations out there so that you've at least been exposed to them. In each of the videos, how we're going to proceed is that we're going to just address a certain number of learning objectives in each video. This series of video lectures is going to address 3 different learning objectives. The first is that we're going to discuss the phenomenon of the electromagnetic traveling wave, which is also called the electromagnetic radiation. Our discussion is going to basically focus on the quantifying of parameters that are used to identify an EM wave, which includes the velocity of propagation, frequency, and wavelength. The second learning objective is that we're going to describe the range of all the possible frequencies of electromagnetic waves, which is called the electromagnetic spectrum. And then we're going to look at how the frequencies of electromagnetic waves changes how they interact with the environment and with electric circuits. So that's the second learning objective. Finally, we'll conclude today's video by looking at the electric field and the magnetic field, which are descriptions of how electric charges and magnetic dipoles affect the space around them. These concepts are really important since current is the movement of charge, and so there's charged particles flowing in current, so there is an electric field that's always there. And then if we have a moving charge by Maxwell's fourth equation, we have to have a magnetic field. So the description of these electric and magnetic fields, stationary fields, is just kind of some of fundamental importance to our understanding. So those are the 3 learning objectives we'll cover today.